and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. In this module we will look at several other circuit parameters of the transmission line. Namely, we will be concerned with input impedance of a transmission line, which will help us solve the problems that are concerned with transmission line circuits. Now, to set a stage for that, let me start with a very simple question. So far, when we have considered the transmission line, we have talked about its characteristic impedance, which really depends on the characteristic or the constants of the distributed constants of the transmission line, that is L and C for the lossless case that we are considering. Given L and C, we can find out what is the characteristic impedance. Given characteristic impedance and the load that the transmission line is terminated in, we can find out the reflection coefficient. From the reflection coefficient, we can find out what is the amplitude as well as the phase of the reflected wave, voltage or the current wave at the load as well as at any other point on the transmission line. However, we have so far not seen how to find V0 plus, which is the amplitude of the voltage that is propagating along the plus Z direction, right. We are assuming that the source is located at some Z is equal to minus L, and then we have a load located at Z equal to 0. In the typical transmission line problems, the load is located at Z equal to 0 and the source is located at a value of Z that is negative. Okay. In that, when we connect the transmission line circuit and we want to understand what is the power carried by the forward wave, what is the power carried by the reflected wave, how much power is dissipated in the load, all that of quantities require us to understand or require us to find what is the value of V0 plus. Now, how do we do that? In order to set the problem, let me start with what I consider it as a paradox, because it shows up that if we completely ignore physical reality, we might land up in situations where we will be in kind of a trouble. We will see what kind of a trouble we will land in. The problem that I want to consider is very simple. I have a source at some Z is equal to minus L. Let us say at some particular distance away from the load I have the source. Let us assume that the source to have no internal resistance, which means that I am assuming that the source is completely internal resistance free, the source is ideal, and let us also assume that it is a pure harmonic source, that is, it will generate a sinusoidal voltage at a particular frequency omega. We will also assume that the line is lossless, okay, and then we terminate the line in not in load, but in our case the load will be a oscilloscope. So, why am I terminating the transmission line in an oscilloscope is because I want to observe what is the voltage waveform at the load end. Okay. So, we will take the input impedance of the oscilloscope to be very high compared to the transmission line, so that we can almost consider the oscilloscope input impedance to be infinity. So, here is our sketch of the problem. I have a transmission line, okay, of some length, right. Let me take whatever the length L be, and because I have chosen the coordinate of the load to be at Z equal to 0 and my Z axis is increasing towards the positive right side, okay, this is how my Z axis is increasing. So, clearly the load is kept at Z equal to minus L, okay. Then I consider this output, right. I take two cables of negligent physical length and then I connect this one to an oscilloscope. Okay. So, I consider this on an oscilloscope in order to display the voltage waveform that I would be observing at this particular terminal of the transmission line. To this, let me connect a source. Okay. As before, I am using these kind of crooked lines to indicate that the size and the shape of these wires do not really matter to me. Okay. So, I consider a voltage source, maybe a slightly better diagram could be drawn here. So, that diagram could be something like this. Okay. So, I have a sinusoidal voltage source here, which in the phasor domain, let us call this as producing some constant voltage. I mean, in terms of the phasor, it is producing a particular sine voltage and hence has a constant phasor, which we denote by Vs with a over bar or with a tilde on top of that one. Now, let me ask you, what is the value of V0 plus? Can I find V0 plus for this particular transmission line? Turns out that yes, I can very easily do that. Because the input impedance of the scope is considered to be infinity, the load impedance for this transmission line is actually infinity. In other words, this is a open circuit load, for which we have already seen in the previous module that the reflection coefficient at the load will be +1, which also means that V0 minus is equal to V0 plus. And if I now consider any particular Z, on the transmission line, any particular point or the terminal points on the transmission line, the voltage at that particular position, which I will label as V line. Of course, this is also a phasor. So, this voltage V line of Z will be given by 2 V0 plus cos beta into Z. Z will be going from 0 to minus L. Okay, that you should keep in mind. Z goes from 0 to minus L, 0 being the load. If you do not recall how we obtained 2 V0 plus cos beta Z, I suggest that you review the earlier modules wherein we have actually derived this particular condition. Okay. Now, what is the line voltage? Line voltage is essentially the voltage at any point on the transmission line. And now let us start approaching the source, which means that Z starts to go from 0 to minus L. At the source point or at the Z equal to minus L plane, if I evaluate what would be the line voltage, it turns out to be some 2 V0 plus cos beta into L. Of course, Z will be minus L, but cosine function being an even function simply gives me cos of beta L, because cos of minus theta is equal to cos theta for a cosine function, right. So, this is the voltage on the line that you would be measuring if instead of connecting an oscilloscope here, I would connect a virtual oscilloscope. No, I wanted to say hypothetical, but I kind of say that I can actually connect a real oscilloscope. So, here I connect an oscilloscope. Of course, I am not connecting in this problem, it is just a notation. So, if I measure the voltage at this terminal, I will actually be able to measure the value of 2 V0 plus cos beta L. Okay. But clearly KVL tells me that at this particular Z equal to minus L, whatever the line voltage that I measure must be exactly the voltage that the source is supplying, which means that this must be equal to Vs bar. Now, here is a simple equation. I was complaining to you that I cannot find V0 plus, but here is a simple equation that allows me to find the value of V0 plus. And what is that value? V0 plus is simply given by the phasor Vs divided by 2 cos beta into L. You can clearly observe that if I change the length of the transmission line, the connection between the source and the oscilloscope, the value cos beta L will also change, which in turn will change the value of V0 plus. Okay. So, what would that V0 plus value be? If I want to look at the magnitude of this one, the magnitude is clearly given by this. Okay. If I consider a very special case of beta L being equal to pi by 2, okay, beta L equal to pi by 2 in transmission line problems is called as quarter wave transformer, because beta we will relate it later on to the wavelength, and it is given by 2 pi by lambda into L equal to pi by 2. If you cancel pi on both sides, turns out to be L equal to lambda by 4, where lambda is the wavelength, which we will just talk about in a few minutes. Okay. So, if you consider beta L equal to pi by 2, what will be the value of cosine function at that point? It would be cos of pi by 2 will be equal to 0, which, and you have a finite quantity in the numerator and 0 in the denominator, clearly making the magnitude of V0 plus go to infinity. Now, if you have so far not been surprised, this is a point where you should really be surprised, because just by connecting an ideal lossless piece of quarter wave transformer between an ideal voltage source and some sort of an oscilloscope or a load with a very high input impedance, I am able to amplify the voltage Vs all the way up to infinity. So, I am actually making a voltage amplifier, okay, just by connecting an ideal lossless transmission line of length lambda by 4. Okay. Now, am I violating some energy conservation principle here? I will leave this as an exercise to you, because I have only calculated the voltages, I have not calculated the current, and I have not calculated the power that is generated by the source and the power that is delivered and the power that is dissipated in the transmission lines. Because I have not taught you how to calculate power, The resolution of this paradox has to wait for some time before we resolve, but the hint is that this kind of a problem arises. The voltage at any particular point on the transmission line can exceed the source voltage, but energy conservation will not be violated, as we will see in one of the exercises. And most importantly, we have considered transmission lines to be lossless, which more or less can be okay for majority of applications, but I simply cannot find an ideal voltage source, because if I could find an ideal voltage source, no matter how much current I draw, I can then have the same voltage terminals maintained at the source output and therefore be able to obtain an infinite amount of power. Clearly that does not happen with any of the voltage sources in practice, because in practice you always end up having a certain amount of source impedance Zs. So this paradox, okay, we will resolve after we understand how to calculate the power, and I will actually leave it as an exercise because there is a couple of calculations that are involved, and I will give you the steps in order to do that one. So this is what I wanted to talk to you about the paradox. Now problems of this nature, I have a source resistance over here, or more precisely a source impedance, because the source resistance, instead of source resistance you can actually have some reactance in the internal impedance of the sources. Therefore I have labeled this by the general impedance notation of Z, and I put a subscript S in order to indicate this is a source impedance. Okay. So given a transmission line connected to the source with its source impedance at one end, and instead of connecting a scope, I might actually connect this one to another load. Okay, this load could be anything. It also includes some reactance to it in general. Therefore I denote the load resistance, instead of load resistance I denote this one by the load impedance ZL. So given this problem, in this case it is not so simple to find out V0 plus. Okay, indeed this problem can be solved by the method that I have described, and the solution actually is slightly more complicated, okay, than what we have already seen over here. The line voltage will have to change. If I consider the original case where ZL is equal to infinity, then the line voltage will be the same, but when you start evaluating the line voltage at Z equal to minus L, you have to understand that there is some current flowing through this, and that current will be the line current, and line current flowing through this Zs impedance of the source will create a certain voltage drop here, and the total voltage that you need to sum will then be equal to the source voltage Vs, that must be equal to the line current at and multiplied by Zs to give you the drop across Zs plus whatever the line voltage. Okay. If you are interested, I can write the solution over here, I can write the solution, and that turns out to be the source voltage being equal to the line voltage phasor evaluated again at minus L into Zs, which is the source impedance, plus the line voltage measured at minus L. This we already know for the case of the scope connection, or for the case where gamma L is equal to plus 1, this is simply 2 V0 plus cos beta into L, whereas this particular case that we have line at minus L will then be equal to V0 plus by Z0 e to the power plus j beta L minus V0 minus divided by Z0, but V0 minus is nothing but V0 plus, therefore that would also be V0 plus, and it would be e to the power of minus j beta L, this entire thing multiplied by Zs. This should be equal to the source impedance Vs. If you actually solve these equations, you will then be able to show that V0 plus, which is the amplitude of the forward travelling voltage wave, turns out to be minus j Vs bar divided by 2 into Zs. Okay. If you are interested only in the magnitude, this would be equal to the magnitude of the source divided by 2 Zs. When Zs happens to be real, then Zs can be replaced with Rs, and you can see that the voltage is kind of split in terms of this Vs divided by 2 Rs. Of course, in an ideal scenario when Zs is equal to 0, which of course cannot exist in practice, voltage V0 plus will go all the way up to infinity, thus giving you the same solution as you obtained earlier. Okay. While this problem was solved, there exist slightly better methods of solving a similar set of transmission line problems, and all of that involve the use of input impedance. Okay. What exactly is this input impedance that I am talking about? Well, consider this transmission line. Okay, I connect this one to a general load ZL. Okay, if I don't make any crooked shapes, it does not mean that I am considering the lengths here as transmission line. It's just that I just did not want to draw crooked lines all over the place all the time. Okay, so I consider this transmission line terminated in load ZL. Let the transmission line have a certain characteristic impedance of Z0. To this I connect the source having an impedance of Zs and generating a certain phasor voltage Vs bar. Okay, how do I solve this problem? In order to find out what is the load voltage, and if you are interested what is the load current will be flowing here, and the load voltage is whatever that you measure across the load. In order to solve what is the load voltage, I need to know what is the total line voltage here, because if I know what is the total line voltage at Z equal to 0, then that line voltage will be exactly equal to VL. In other words, if I know what is the line voltage phasor at Z equal to 0, this would be equal to the load voltage phasor. Okay, so this is what I need to know, but line voltage evaluating this at Z equal to 0 will require me to know what is gamma L. Of course, that I can find out because ZL is known, Z0 is known, but this will also involve the constant V0 plus, which you need to solve or which you need to find out, and the solution is not the same as this one. This was a special case of solution where gamma L was equal to plus 1. In the general case where gamma L is not equal to plus 1, then this V0 plus will also not be the same as here. Okay. So, to solve this problem, what we do is we develop impedance or the concept of an impedance at every point on the transmission line. What do I mean by this? See, at every point on the transmission line there is a certain line voltage, right. So, there is a certain line voltage that I can, and this line voltage is a phasor of course. So, this line voltage will be there at every point on the transmission line, which will be the sum of forward as well as backward travelling voltage waves. Similarly, there will be a current phasor as well at every point of Z, and that would also be the sum of forward as well as backward travelling current. Now, if I were to form the ratio of the line voltage at any point on Z to the line voltage at the same point on the Z, then this gives me what I call as the line impedance, and line impedance is also changing with Z. Okay. Now, I can find the line impedance here, I can find the line impedance here, and I can keep coming towards the source. Okay. And at some particular point where Z is equal to minus L, I can find out what is the line impedance here. The line impedance at the source point where Z is equal to minus L is what we will call as input impedance of the transmission line. Okay, or input impedance as seen by this particular gentleman, which is this generator will see this input impedance, okay, when I terminate the transmission line of some length L, okay, with the load ZL. In other words, the load impedance at ZL has been transformed away into and made to look as though the load impedance is actually equal to Zin, which is the input impedance. So, what is the advantage of this? The advantage of this is very simple. Once I have what is the input impedance, I can then use my standard circuit theory to simplify this scenario and then find out what is the, so this would be my input impedance. Okay, I can easily find out what is the initial voltage or V0 plus from these expressions. I will demonstrate that to you very shortly. Okay, so this has the advantage of replacing this complex loads ZL by an equivalent input impedance that is seen at the transmission line source end. So, what is that input impedance? How do I calculate it? This requires that first we define what is the line impedance. So, our definition of the line impedance was that and this line impedance of course varies with at different points on the transmission line. So, this is nothing but the line voltage phasor to the line current phasor. Now, at this point there is a bit of a caution. The characteristic impedance of the transmission line was defined not in terms of the total voltage phasor or the total current phasor, but this is defined in terms of the amplitude of the forward going voltage to the amplitude of the forward going current, or it was defined as minus V0 minus divided by I0 minus, where V0 minus was backward travelling voltage wave, I0 minus was also travelling in the backward direction. Okay. So, this is the characteristic impedance, which, and if you want to find out what is the characteristic impedance, you have to assume that either there is a forward going voltage and current or backward travelling voltage and current. Okay. This is completely different from the line impedance, because line impedance actually is the sum of the total forward plus backward voltage to is a ratio of sum of the backward and forward voltages to sum of forward and backward travelling current waveforms. Okay. So, please note this difference, this is very important. So, let me mark this importance by drawing this cartoon. Okay. Yes, now that we have line impedance, of course I do not really have it, I need to substitute for V line and I line, then I can evaluate this at Z equal to minus L in order to find out what is the input impedance. I will not derive the complete expression for this, it is not that it is difficult, but it is just that little bit of tedious algebra is involved, but I will give you the step from which you have to do couple of additional algebraic steps to arrive at the final solution. Okay. So, the line voltage phasor is given by V0 plus e to the power minus j beta z, remember V0 plus is the amplitude of the forward going voltage, plus V0 minus e to the power plus j beta z, because plus represents a voltage wave travelling in the minus z direction, divided by the line current, which happens to be V0 plus by Z0 amplitude e power minus j beta z minus V0 minus by Z0 e to the power j beta z. You can then substitute for V0 minus gamma L into V0 plus and substitute for gamma L as ZL minus Z0 divided by ZL plus Z0. Substitute these two expressions into this above line impedance equation and then evaluate the line impedance at Z equal to minus L. What you will end up with the input impedance expression, then you will end up with the impedance expression which is given by Z0 ZL cos beta L plus j Z0 sin beta L divided by Z0 cos beta L plus j ZL sin beta L. Okay. So, you will end up with this particular expression for the input impedance. This occurs quite frequently in the transmission line problems, therefore, I will mark this in a very special way. There is an alternative way of writing this that involves taking cos beta L as a factor out. Okay. So, that will go in the numerator as well as in the denominator, and sin beta L over cos beta L can become tan beta L. So, the alternate form of writing this one will be Z0 ZL plus j Z0 tan beta L divided by Z0 plus j ZL tan beta into L. Okay. Incidentally, beta into L is called as the electrical length. Okay. Beta into L is called as the electrical length, and this electrical length can vary from 0 to 360 degrees. Okay. That is when beta L goes from 0 to 2 pi. This would be the electrical length variation. Okay. What use is this input impedance expression? We will have lot more to say about the input impedance later on. Okay. For now, what we want to do is to solve a problem where this concept of input impedance will be required for us. Okay. So, let us try to do that one. Okay. The idea is that once I know what is the input impedance, I can then find out what would be V0 plus, and then I can find V0 plus from these expressions and therefore solve for what is the voltage that is dissipated in the load. Okay. So, in order to do that one, let me consider a problem with some numerical values out there, and I would suggest that you independently verify the solution that I am going to present now. The problem is simple. We have a real internal impedance of the source, which is 25 ohms, which is connected to a voltage phasor. So, the voltage that is supplied, the source voltage is given by 10 cos omega t plus 30 degrees. This can be replaced in terms of the phasor notation as 10 e to the power j 30 degrees. Okay. So, this is the phasor, and this phasor happens to be a constant, and that is connected to the transmission line. So from here onwards we have a transmission line whose length is lambda by 4. Now lambda by 4 means that beta into L must be equal to pi by 2 or 90 degrees. Okay, I am writing the equal sign here, but you understand that this is in radians and this is in degrees. Okay. Now when I terminate this transmission line with a real impedance of 100 ohms or a resistance of 100 ohms, and I now ask what should be the voltage that is dissipated in this one, I can easily find out, or what is the voltage across the 100 ohm impedance, I can easily find that out. In order to do that, I need to transform this 100 ohm input impedance, sorry 100 ohm load impedance into a certain input impedance, correct? And in order to do that one, I need to go back to the expression for input impedance, which happened to be Z0 into ZL plus j Z0 tan beta L divided by Z0 plus j ZL tan beta into L. But what is tan of pi by 2? It is actually infinity. Okay. And our mathematician friends will tell us that when this tan beta L is becoming very large, okay, then I can neglect this ZL in comparison with tan beta L, or in comparison with jz0 tan beta L, and similarly I can neglect z0 in the denominator with respect to jzl tan beta L. So if I make these approximations, I will end up having the input impedance given by z0 square by zl, okay, because j and j cancel, z0 into z0 gets multiplied and you get z0 square and divided by zl, and this value will be equal to 25 ohms. You can also show that the load reflection coefficient is 1 by 3, 100 minus 50 divided by 100 plus 50. I did not mention that the characteristic impedance was 50 ohms over here. Now that I have this equation, right, or I have simplified this input impedance, right, I can find out what is the initial voltage phasor. The initial voltage phasor will be, the equivalent circuit will be that this is the source, this is the 25 ohm input internal impedance, and this is the 25 ohm impedance that is the equivalent impedance of the transmission line circuit. Okay, so input impedance with 25, and the current phasor will clearly be 5 e power j 30 amperes. Okay. Now I can find out what is the line voltage, right. I know what is the line voltage expression, which happens to be V0 e power j beta L plus gamma L in this case will be equal to 1 by 3. So V0 plus e power minus j beta L. I know what is beta L, which is pi by 2, therefore this becomes j and this becomes minus j. Okay. I can take this V0 plus e power j beta L as a common factor and then end up having 1 by 3 e to the power minus j 180 degrees. This beta L is nothing but 90 degrees. This should then be equal to whatever the current that is getting multiplied, and this should then be equal to, sorry, this is the voltage that I have. The current that I get is Vs by 25 plus 25, that is the voltage, and multiplied by 25 will give me the total voltage that I seen across this input impedance. So Vs was 10 e power j 30 degrees and this was 50 degrees. See, this was 50 ohms, therefore this turned out to be current of 5 e power j 30, but this has to be multiplied by 25. So this is the continuation of the problem. I made a very small mistake. The current that you would see across this particular, I mean through this particular circuit, will be the voltage phasor divided by 25 plus 25, but I am not really interested in the current, but I am interested in what is the voltage that is developed across this 25 ohms, which then can be obtained by multiplying the current by 25. So if I multiply I by the input impedance of the transmission line, I get what is the input voltage phasor. So I call this as the input voltage phasor, which appears at the equivalent input impedance of 25 ohm, and this is equal to 5 e to the power j 30 degrees. Okay. So this input impedance of course must be exactly equal to the line phasor that we measure at minus L, and we know that the line phasor measured at minus L will be of this form. This is the forward going voltage, this is the backward travelling reflected voltage, Okay. So, and this backward travelling reflected voltage is multiplied by 1 by 3 because that happens to be the reflection coefficient for this problem. Okay. So, I can take this V0 plus e power j beta L common. I know beta L is 90 degrees. Okay. And if I take 90 degrees out, this becomes e to the power minus j 180 degrees. E to the power minus j 180 degree is nothing but minus 1. So, this term is actually 1 minus 1 by 3 V0 plus e power j 90 degrees, that must be equal to 5 e power j 30 degrees. So, this is the voltage, right. Now, I can take this e power j 90 degrees onto the right hand side. So, this becomes e to the power minus j 90 degrees when it goes to the right hand side, and this becomes 5 e power minus j 60 degrees, and V0 plus will be this 5 e power minus j 60 degrees divided by 1 minus 1 by 3, and this happens to be exactly equal to 7.5 e power minus j 60 degrees voltage. Okay. What would be the load voltage? I can find out what is the load voltage by evaluating what is the line voltage at 0, right. But the line voltage at z equal to 0 will be given simply by V0 plus 1 by 3 V0 plus. I have taken the liberty of writing gamma L as 1 by 3 because that is the case, that is the value in this particular case, and this must be evaluated. Now, it is very easy to evaluate because I know what is V0 plus, which happens to be 7.5 into e to the power minus j 60 degrees, and then if I take 1/3 of this and add it to the same value, what I get is 10 e power minus j 60 degrees volt. You might be surprised to see that the load voltage is exactly equal in magnitude to the source voltage. That is, the load voltage, this is actually VL of phasor, right. So, this is the VL phasor. So, the magnitude of the VL phasor is exactly equal to the magnitude of the source voltage. Okay. That magic has actually happened because we considered line to be lossless. Okay. Because we considered line to be lossless, all that the line did was to delay whatever that was to be delivered to the load, and that essentially is the reason why you get the load voltage magnitude to be the same as the source voltage. However, there is a phase difference between the two, right. This phase difference between the two appears because of the propagation delay associated with the transmission line. We had a transmission line of effective length beta L equal to 90 degrees, and we initially started off with a source voltage that had a magnitude of 10 volt, but at an angle of 30 degrees with respect to the x axis, okay, in the phasor representation. But after delay by 90 degree, which corresponds to rotation in the counterclockwise direction, okay, the value of the load voltage will be at 10, which will be the same magnitude, but it would be at 60 degrees below x axis. The total phase shift between the source voltage and the load voltage will be equal to 90 degrees, and this 90 degree phase difference is introduced by the transmission line. So, with this we finish this module. I suggest again that you look at these numbers and understand carefully as to what steps that were involved. I have made a couple of numerical errors while describing the solution to you, but the final answers are all right. You can just verify this one once more. So, with this we thank you.